think I figured out how to do the audio volume a little better this time. Anyway, this problem involves a buffered solution, number 18. So you're probably going to want to think about the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log of the conjugate base over the concentration of the acid. All right. So in this particular problem, the acid is this. So that's going to be the concentration that goes on the bottom originally. And this is the base, the conjugate base. So that's going to be the concentration on the top, or in other words, the salt. But you'll notice it doesn't really want us to calculate the pH at equilibrium, or excuse me, it doesn't really want us to calculate the pH in the buffered solution. It wants us to calculate the pH after you add these two amounts of things. All right, so let's start with situation A. In situation A, you're adding that many moles of NaOH. The nice convenient thing about this problem is that it tells you that it's 1 liter of solution and that there's no change in volume, so that means that 0.080 moles of NaOH is the same thing as 0.08 molar NaOH. When you add the NaOH, it reacts away with the acid. So that means for every amount of this of NaOH you add, that's going to subtract from the acid and add to the base. So when you subtract from the acid, you're going to get the original amount of acid, which is 1.00 molar acid of the HA, and you're going to subtract the 0.08 molar. So that's going to be the amount of acid right there. The amount of base is going to be the 1.00 molar, excuse me, the conjugate base. This is the salt. It's the A minus, and you're going to be adding to that. The reason that you're subtracting from the acid and adding to the base is because when you add sodium hydroxide, it's going to react away acid, and it's going to make more of the conjugate base, because once the acid has the H taken away, it becomes the conjugate base. So that goes in the numerator. As for the pKa, well, we have this whole fraction figured out then. But the pKa, we don't know. You got to look it up. I found it in the textbook on page number 680. So on page 680, I found that the Ka of this acid, which is acetic acid, is 1.8 times 10 to the negative fifth times 10 to the negative fifth. So that means that the pKa is 4.74. You just take the negative log of Ka, same way as you would take pH. P means power of, or so the negative log of. All right, so now that we got that all figured out, it's just a matter of plugging and chugging. So we get pH is equal to 4.74 plus the log of 1 plus 0.080 and over 1 minus 0.080. Again, because the NaOH is going to add to the conjugate base, it's going to take away from the acid. Do that all out, and we get the pH is equal to 4.81. All right, that's A. B is pretty similar. In B, though, you're adding HCl. So this time, every HCl bit you add is going to actually increase the amount of HA. Because what's going to happen is, as you add HCl, whatever A minus is in there, if you add HCl to the container, it's going to want to reform the HA. Remember, this is a weak acid, so pretty much it doesn't want to dissociate. If there's extra H's around, they're going to latch right onto the A minus, and they're going to reform HA, and the HA isn't going to want to break apart again. So I think you guys can do B on your own after I've shown you how to do A on this one.